We have these things called acids and bases, and we have to know what is an acid and what is a base and be able to recognize what we're looking at. And so the first thing is that acids produce H plus or H3O plus. And H3O plus is known as a hydronium, and the H plus is known as a proton. Now, acids also are H plus donors. Okay, more on that in a bit, but basically you're moving an H from one molecule to another molecule. And if you're moving it, then you're donating it. So it's an H plus donor. Okay, now how can you tell if you have an acid? Well, the big giveaway is if it has an H in the front. So these are two acids, it's hydrochloric acid and sulfuric acid. And if you look, what's the same about both of these? It has an H in the front. Now, a base, on the other hand, produces hydroxide, which is OH minus. They produce OH minus, which is the hydroxide ion. And just like with an acid is an H plus donor, then you're going to have an H plus acceptor. Okay, so acids produce H plus or H3O plus and H plus donors, and bases produce OH minus and they're H plus acceptors. Now, the way you can tell that you have a base many times is because it's going to have the hydroxide on the back end. Here are a couple of bases. And note that the hydroxide is parentheses 2 on the calcium hydroxide. That means it's going to produce 2 hydroxides as a base. And we can see what makes a base is it has OH minus on the end. That's how you can tell. So if you're looking at a compound and it has an H in the front, then it's an acid. And if you're looking at a compound that has an OH on the back, it is a base. Now, when we get into organic acids, then we have these things that are going to look like this. And that is with organic acids, that's acetic acid, we have H on the end. For right now, let's just concentrate on having the H in the front for acids and bases. Now, how does that work when an acid is in water? And the way it works is like this. Generally, if an acid is in water, then what it will do is it will donate the H plus onto the H2O, and you'll be left with the Cl minus that's left over, and now you have an H3O plus, the hydronium ion. And so the hydrogen was donated to the water, and that made the water become H3O plus, okay? And so this is an acid since it donated an H plus, and since this is an acid, then the water becomes a base since it accepted an H plus, okay? Now, a lot of times we can also write this as HCl just simply dissociating into H plus Cl minus. And that's what happens, but the H plus never really exists in the water. It actually goes from the HCl, hydrochloric acid, to the water, okay? Now, you can also have this sort of situation where you have sulfuric acid reacting with water, and the same situation is going to happen. The H in front of the H2SO4 is going to be donated to the water, and that'll make HSO4, the bisulfate ion, since it just lost the H plus the hydronium H3O plus. And we can also write this, if we're just focusing on the dissociation of the strong acid sulfuric acid, we can say it dissociates into H plus plus SO4 minus HSO4. And then that can also dissociate that extra proton that's right there into another H plus, so that you end up with two H pluses plus the sulfate ion. Okay, both of these are legitimate ways of writing the dissociation of sulfuric acid and also above the dissociation of hydrochloric acid. Okay, so that's what happens to the acids when they are dissolved in water. They dissociate into H plus whatever the anion is. In the case of HCl, that's Cl minus, the chloride, or in sulfuric acid, that in that case it's H plus and the sulfate ion, ultimately with the two hydrogens. So this is what's happening in water when acids dissociate. Now bases, on the other hand, are a little bit different. And so we start out with a base. Here we go. We start out with a base, and it will dissociate into the ion plus the hydroxide. Okay. And we can also do, say, calcium hydroxide, and it will dissociate into calcium 2 plus the two hydroxides. Okay. Now we can have a situation where we have a hydrogen acceptor that's going to behave as a base. And let me draw you an example here. Let's take ammonia, NH3, plus water. And if you notice, this one does not have an OH minus attached to it. NH3 is a base, but it's not an OH producer. It's a Bronsted-Lowry base, and so it's going to accept the hydrogen from the water. Now remember, the H plus is positive, and so it's going to make that NH3 into an NH4, and now since it's got an extra hydrogen on there, it becomes positive, and the piece that's left over from the water is the OH minus. So in this case, the ammonia is the acceptor from water, and so that makes the ammonia the base, and it makes water the acid. Now, if you noticed on my previous examples of, say, sulfuric acid and hydrochloric acid, when they produce H plus, they donated it to the water, and they made water an base. And so water is what's called amphiprotic, which is just means, all it means is that it can behave as an acid or a base. And so water is amphiprotic. And so when you work examples out of your book, many of them are going to use water. And what you have to do is you have to count the number of protons or H pluses that are moving from one to the next. So you are accepting if you get more H, and you're a donor if you have less H. Okay, so let me show you another example, and we'll compare the two. Okay, so let's say we start with the ammonium ion, and we have H2O, and we end up with ammonia plus H3O plus. Okay, and what's happened here is that the H plus has been donated to the water. Now let's compare these two. Now we'll go back up here to the NH3 up above, and we said that was a base. Well, how many hydrogens are on that ammonia? And we say there's 3 hydrogens on the ammonia, but when we look over here, we see 4 hydrogens on the ammonium. And so what does that mean? That means that the NH4 gained, pardon me, NH3, the NH3 gained as it went from left to right. So that makes this a base. And we look at the H2O, and how many hydrogens does it have? It has, switch colors here, it has 2 hydrogens. And we look over here at the OH minus, and it has 1 hydrogen. And so it went from 2 to 1. Therefore, H2O lost. So it's an acid. And we look down here at the bottom. Similarly, we go from 4 on the NH4 to 3 on the NH3. And so what does that mean? That means we lost. And so NH4 plus, the ammonium ion, lost. And that makes it an acid. And then we look at the H2O and we say 2 on the H2O and 3 on the hydronium H3 plus. And we look there and we say, well, you know what? The H2O gained. And so therefore, in this case, the H2O is a base. And so those are Bronsted-Lowry acid-base reactions, okay? One of them is going to end up being an acid. One of them is going to end up being a base. And what you have to look for is which one is gaining hydrogens going from one side to the other, in which case it's a base. And you have to look at which one is losing hydrogens going from left to right. And in that case, that's the Bronsted-Lowry acid. And the one thing I do want to point out, though, is that the acid and the base are always reactants. They're always reactants. They're on the left-hand side of the arrow. So you never want to say the right-hand side is the Bronsted-Lowry acid or the right-hand side is the Bronsted-Lowry base. And by the way, if you have an acid in these Bronsted-Lowry equations, if you have an acid, you're going to have a base. And if you have a base, you're going to have an acid.